All right, we are up to video number 3 on groundwater. This is going to be about permeability, and we are on page 21. All right, how does water move through a soil sample? Okay, permeability describes how fast water will move downward through the soil. Okay, it's also can be referred to as the rate of infiltration. Infiltration is a word we used earlier, which refers to water flowing through the soil. So the rate of infiltration is permeability. It just describes how quickly or how fast the water will seep through the ground and into the deeper ground. Okay. There are certain factors that affect permeability. Porosity is one of them. Typically, when a soil sample has more airspace, it allows the water to flow through that soil sample more quickly. So if you look right here at sample A, okay, we have soil sorted. The water will basically be able to just kind of weave in and out like that, and it will move through faster than it would move through down here where there are mixed and unsorted particles and the porosity is lower. Okay, so when the porosity is greater, typically the permeability is also greater. Second thing is the particle size. The larger the particle size, the greater the permeability. Let's take a look. Okay, in this case, the porosity of this sample and this sample is actually the same. If you recall, the many small holes and spaces of pores are equivalent to the volume of the larger but not as numerous air pockets over here. So the porosity is the same. Now the permeability is greater over here for one simple reason. As the water is poured down this way, okay, I'll show you right here, the water is able basically to just zigzag, and the zigzagging does slow it down, but if you look over here, and I know I didn't draw it perfectly, but it has to zigzag even more. So the fact that this has to zigzag even more round and round and round and round all these little particles will slow down the rate of flow, making it less permeable, whereas this one will be more permeable and the water will get through faster. Okay, so this one over here is greater permeability, and this one is lower permeability. All right. This is just a chart, we'll talk about it later on, of the different size particles. You're probably very familiar with sand. Sand runs anywhere from 0.006 to 0.2 as a size, centimeters. Pebbles are larger, cobbles are larger, and boulders are basically big rocks, and you will see this more later on. Okay, capillarity is something that is interesting. Okay, capillary action is the upward movement of water through the soil opposite of gravity. Okay, you typically don't notice this as obviously as you might notice water going down, but you can see it in certain places. Okay, this just shows a person climbing up a wall. The reason they're able to climb up the wall is because the wall is relatively close to the person. It's a small space. So the point here is that the smaller the space is, the easier it is for this person to move up. Okay. In a similar way, that's me. The idea here is that capillary action, or the ability of water to move upward to the soil, is increased if the particles are smaller because the spaces between the particles are smaller. So here, where the space between the walls is small, I was able to, fit myself in between and then climb up the wall. If you look really closely, you will see Mr. Rosencrantz smiling through the window. I didn't even realize he was here until I looked at this picture several years later. Okay, now to show you what I'm talking about, I'm going to have you look at this video, which was pretty cool. I'm going to forward it to a certain point.
Capillary action is very important for moving fluid in our bodies. Have you ever heard? You can see the water traveling.
Now, I want you to look.
Then I arrange the towel so only the very bottom of the towel will get wet.
What she's doing,
making sure that the marker line is above the level where the.
Okay, now what she's about to do is she took a paper towel and she drew a line on it. Now a paper towel is not a solid object, meaning that there's air spaces in these particles are all weaved together. If you were to hold a paper towel up to your face and blow, you would be able to feel the air, all right? There are actually little tiny air spaces in it, but the spaces are very, very tiny. So what she did here was she drew a black line with a magic marker, and she's going to dip this into the water, but only right below the line. And you're going to be able to see the water rising up the paper towel. Okay, that is an example of capillary action. So let's just watch.
Water will be. As soon as the paper towel gets wet,
Here we go. See the
you
water?
can see the water traveling up the towel. And look what happens to the ink. It's moving too. This takes several minutes, so we'll speed up the video so you can get a better look. And check.
So what I want you to get out of this is that when this is just dipped in the water, which is down here, the water is able to travel up through the tiny spaces against gravity. Okay, that is capillary action. And it happens in the soil right at the very top of the water table in a place called the capillary fringe. What I really want you to get out of this is that capillary action occurs most strongly when the soil size, the particle size of the soil is very tiny, because then the spaces between the particles are very tiny. Okay, so it works much better in a fine grained soil than it does in, say, pebbles. Okay, so that's just something I wanted to watch. I do it in class, but we're not there, so I'm trying to do the best that I can. All right, so the smaller the particle size, the greater the capillarity, sometimes referred to as capillary action. All right, capillary action is also what allows people to use colored dyes and color carnations, because the colored water will move its way up through the stem and end up in the white flower, changing the color of the flower. So it's kind of a cool thing. Okay, water retention. Okay, that just means water retained. All right, the smaller the particles, the greater the water retained. So in other words, as water pours on the ground and then infiltrates through the soil, okay, most of the water will pass through, but some of the water will remain on the soil particles, keeping them slightly damp. Okay, this is saying the smaller the particles, the greater the amount of water retained. Let me try to explain why this is. Okay, let me just try to draw you a picture here. Okay, it's pretty straightforward. Let's just say that represents one soil particle. Okay, and let's say that we have the same amount of particle, the same mass, but I'm going to divide it into a few different size pieces. Let's just try to, love how this is not working all that great, but I'm going to try. Okay. All right. Now, can we agree that these four particles that I drew, if you put them all together over here, are basically the same mass as this? Okay. Now, the reason why these smaller particles will retain more water after the water passes through compared to this is one simple reason. Okay, there are more surfaces for the water to stick onto here, because you have all of these inside parts that were not available over here, right? So over here, what you basically have, you have a surface over here, you have a surface over here, a surface over here, a surface over here, this one, okay? Compared to this, where there are also additional surfaces in all of these inside areas over here and over here, okay? So that's why when the water passes through the soil, if the soil particles themselves are smaller, there's actually more surface area for the water to stick to. It's kind of like saying if you jumped in the shower and then you got out of the shower after the water stopped running, you would not immediately be perfectly dry. The water would stick to the surface area of your skin and the little hair particles and things like that. Okay, so many smaller particles have a greater surface area for water to stick to. Okay, now let's just look at this and do a quick review. Okay, for porosity, which one of these two containers has the greater porosity? Now this is sort of a trick question, because if you said the answer is neither of them, or they're both the same, that is correct. Okay, the number of air spaces here, the total volume of air spaces is equal here. Many tiny tiny spaces here compared to less but larger particle and air spaces here make this equivalent. So the porosity, the percentage of airspace is the same. Permeability, which one will the water flow through more quickly? Okay, if you said B, that is correct. Okay, the water will come down like this and it'll just be able to kind of zigzag relatively quickly, as opposed to this one where it has to zigzag and zag and zig and zag and zig, and kind of doing the best I can with my finger here on my screen, but that would take longer. So the permeability is definitely better over here in B. In terms of capillarity, which one of these two will allow the water to move upwards the most? Okay, hopefully you said this one, because the smaller particles have smaller spaces. It's easier for the water to latch onto the sides and basically work its way up, if I simplify it using kind of a metaphor. Okay, water retained, as the water pours through this way. Okay, and as the water pours through, I'm going to just erase that for a second because that did not. Right, as the water basically comes through here, and as the water comes through here, if you were to open up the bottom and allow the water to flow out, which particles would have the most water on them after you let the water flow through? And the answer is A. Okay, because there is more overall surface area and the water is sticking to and retained by the surface area. Okay, all right, now we're going to, if you turn to page 22 and 23 in your notes, you are going to see a bunch of practice questions. I want you to try to do those questions now, and then we will be back for the final lesson on groundwater in a minute. All right, guys. Thank you.